welcome back to this session. So this is the last lecture of this module, potential flows. Okay, so we have left out with some parts of the rotating cylinder case. So we will see that portions which are left over, and we will solve some numericals in this. Okay, so this is the last lecture, and these are the two things: flow past rotating cylinder, continuation what we have done, and some part of numericals. Okay, so let us see. Let us quickly revise before we move ahead. In the case of flow past rotating cylinder, we have seen for flow past rotating cylinder, flow past rotating cylinder, flow past the rotating cylinder, we have seen the velocity potential function f of z in this case is uz plus u a square by z plus minus I times of circulation by 2 pi into log z to the base e. So this is the complex potential function that we talked about. Okay, now we have split this into a velocity potential function and stream function. Okay, and also we have talked about some radial component of velocity and the theta component of velocity actually. So we have seen this u r is equal to the radial component of velocity is equal to u times of 1 minus a square by r square times cos theta, and u theta is equal to minus u times of 1 plus a square by small r square sin theta plus circulation by 2 pi r, correct? Circulation by 2 pi small r. I think this is the equation if I am not wrong, correct? So capital U times of 1 minus a square by r square into cos theta minus u times of 1 plus a square by r square sin theta plus this circulation component, which is circulation by 2 pi r. So now let us continue here. So we have seen these equations, and then we talked about the case of stagnation points. Okay, so stagnation points, we talked about the case of stagnation points. Okay, so normally to identify the stagnation points, we have at r equal to a and sin theta is equal to circulation by 4 pi u a is what you have here. Okay, so when you solve this, you will get two values of theta, then definitely you will get two stagnation points on the surface of the cylinder. So basically, if you see, if this is the cylinder, then if this is revolving in anti-clockwise direction, for example, then the flow goes like this, and the flow actually goes in this particular way. Okay, so these are the streamlines in this case, because whenever the fluid is trying to move, and this cylinder will try to push back the fluid again, okay, because of the inertia. So that's why this fluid here, the velocity, the streamlines are almost flat here in this case. Okay, so this is the rotation in the anti-clockwise sense. So in this case, we observed that the stagnation points will be at this location. Normally the stagnation points will be in such a location that this is theta. If this is theta, then this is also theta again. Okay, so this angle is also theta. So this is the first stagnation point, and this is the second stagnation point. Okay, and here if you take the velocity profiles, then we have this and like this. Okay, and finally what happens when the circulation of the cylinder increases? These two stagnation points will come and meet at one particular location. So you have only one stagnation point in that case. Okay, so for a single stagnation point, for single stagnation point, for single stagnation point, for single stagnation point, your u theta is basically equal to 2 times of u stream velocity, which means this implies, u theta is basically a times omega. Rotational speed of the cylinder should be equal to 2 times of this velocity. Okay, look, this is the case when cylinder is evolving in the anti-clock direction. Let us suppose if cylinder is evolving in the counterclock, means in the clockwise direction, then the shape will be reverse. Okay, means this streamlines will actually come here, stagnation points will come here, and this smooth curves will actually shift to the top. Okay, it completely depends upon the rotation of the cylinder actually. Clear? This is the diagram only when the rotation is in the anti-clockwise sense. If rotation is in the clockwise sense, then these two stagnation points, they actually come to the bottom here. Then this flatness of the streamlines will come to the bottom, because flow will try to move in this direction, and when this is in clockwise direction, cylinder will try to push the flow in this. So flatness of the streamlines comes on the downside, and this smooth streamlines will come on the top. So these things has to be recorded actually. Okay, So these are the points that we talked about in the previous session. Clear? Now if you see, so if we continue, look, we have this cylinder which is revolving at some angular velocity omega, let us say. Then in that case, you have some streamlines which are flowing like this. Okay, so these are the streamlines that you have. Okay, this is at free stream velocity u, and this cylinder is rotating at some angular velocity omega. Now again, if you apply Bernoulli's equation, if you want to talk about this coefficient of pressure Cp, coefficient of pressure which is Cp actually. Okay, so coefficient of pressure Cp is basically Cp is equal to P on the surface minus P infinity by half rho u infinity square in this case. Okay, so now let us see, in this case you have this rho u square actually here. Now if you apply Bernoulli's equation at 2 points, for example, say the 2 points are somewhere here like this on the surface and on the one point here which is at far and one point on the surface of the cylinder. Okay, so if you apply Bernoulli's equation, applying Bernoulli's equation between the points 1 and S, between the points 1 and S. Okay, so if you do this, then P1 by rho z plus V1 square by 2z plus Z1 is equal to PS, pressure on the surface of the cylinder, by rho z plus Vs square by 2z plus Zs is what you have. Okay, now since you have taken on the same horizontal datum, these two Z gets cancelled. Okay, and G gets eliminated in all the equation in the remaining 4 terms. Now what about V1? At this location 1, V1 is same as free stream velocity, and Vs is equal to, now here radial velocity is 0, okay, because on the surface of the cylinder there is no radial velocity. Whenever you keep r is equal to a, then definitely this term, sorry, where is this? Yeah, this term ur goes to 0 when you put r equal to a. So we have only this u theta is equal to Vs is equal to minus 2u sin theta plus circulation by 2 pi r. Correct? So this is what you have here. Okay, so 2 pi a actually on the surface of the cylinder you have taken, so radius value is a, so circulation by 2 pi a, correct, minus 2 times of sin theta plus circulation by 2 pi a. This is what you have for the Vs. Okay, because u r is 0, so whenever u r is 0, total magnitude of velocity is nothing but same as u theta, so that's why we have this. Now if you replace here, therefore Ps and P1, what about P1? P1, if you take P infinity, then this equation turns out to be P infinity minus Ps, or generally Ps minus P infinity, Ps minus P infinity by rho is equal to, so Ps minus P infinity by rho is equal to V1 square minus Vs square by 2, which is u infinity square minus u theta square by 2, okay, which is u theta. U theta is same as us. So if you divide this half, if you multiply this half here, for example, if you bring this half to the left hand side, and if you take u theta square, so Ps minus P infinity by half rho u infinity square is equal to 1 minus u theta by u infinity whole square. Now what about u in theta by u infinity? This is a big expression, you have to do little carefully. So Ps minus P infinity by half rho u infinity square is equal to 1 minus, so what is u theta by u? If you divide this complete expression with u, you have to use 2 sin theta again. Okay, so 1 minus, this expression gives you psi divided by 2 pi ua, this circulation divided by 2 pi ua minus, if you divide this with u again, this u gets cancelled, so 2 sin theta. Okay, so minus 2 sin theta whole square. So this is the expression for the calculation of pressure in this case. Okay, so 1 minus circulation by 2 pi u square minus 2 sin theta, this divided with whole square actually. Okay, so because u theta is this expression, because this is same as u theta on the surface of the sphere, on the surface of this cylinder, so minus 2u sin theta plus circulation by 2 pi a. If you divide this with u, then this u gets cancelled and u comes in the denominator. So that's how we have this particular expression. Okay, so this is the case for the ps minus p infinity. Now depending upon the circulation value, all these things, you can get the pressure variation. Okay, so for example, you can take whenever circulation is equal to, like in previous case we have seen, for the case of single stagnation point and all, this circulation has one particular value. Okay, so circulation is equal to 4 pi ua, we have seen all these things. But right now let us suppose this is the expression that is with you. Okay, now if you want to calculate the force acting on the cylinder actually, okay, then let us see how to evaluate the cylinder, force acting on the cylinder. From this equation, force acting on the surface of the cylinder is equal to P infinity plus half rho u infinity square times of 1 minus circulation by 2 pi ua minus 2 sin theta whole square. Okay, so square of this. So this is the expression, correct? So this is the expression for the pressure acting on any location on the surface of the cylinder. Now if you want to calculate the lift force, then like in the previous case, you have the cylinder, then there is some pressure which is acting ps at some angle theta. For example, this is the reference, theta equal to 0, this is center, so there is some ps actually here. Okay, now whenever there is some ps, then let us calculate the total lift that is getting generated in this case. Okay, so let us do this. So you take some cylinder here, let us try to write the expression carefully. You take the cylinder, so when you take the cylinder, this is center for example. Okay, so this is center. Now if you take small strip, for example somewhere here, if you see, if you take some small strip like this is radius r and this is of d theta. Okay, so that this length which is here, is r times of d theta. Okay, so the length which is here is r times of d theta, and there is pressure force which is acting at some angle theta. So there is pressure force ps that's acting here, ps, and let us suppose this is acting at an angle of theta. So this tip is at an angle of theta, for example. Okay, now if you draw the case like in the previous case how we have done, if you take the surface of the cylinder, okay, generally if you take the length of the cylinder L, so if you take the length of the cylinder L for example, so if you take for example, then this is the surface on which there is some pressure force, correct? So this is the top surface on which there is some pressure ps. Now this is d theta and this is r, then this length is r times of d theta and this is length L. Okay, now on this top surface the pressure that's acting is ps. There is some pressure which is acting basically here, so the pressure that's acting is ps actually, or from the top you can denote this. So ps is the pressure that's acting on the surface. Now this total lift, or generally if you see ps is in this particular direction, so on this small elemental area dA, the pressure force that's acting is ps into dA, correct? Now if you take the angles, the resolution, then you know, since this angle between this line and the horizontal is theta, definitely this angle is 90 minus theta. Okay, so this is 90 minus theta. So therefore this force is PS dA into sine theta. Clear? So this is the bottom force or the downward force that's actually acting at this on the small part of the cylinder. Okay, now if you want the total force, you have to integrate this particular expression. So if you integrate, lift force acting on the cylinder is equal to lift acting on the cylinder, lift acting on the cylinder is equal to integration of this df sine theta or PS dA sine theta over the complete area. Okay, or the complete area. Now, and this is in the bottom direction, so definitely we have to keep a minus sign here. Okay, this minus sign is there because this is in the bottom direction, minus PS sine theta, minus PS dA sine theta. Okay, this negative sign is due to the downward direction of this component. Okay, now what is PS? We have this expression, PS is equal to this expression, this expression which is here, PS is equal to P infinity plus half OU infinity square 1 minus this complete term is the pressure at any location on the surface or at any location on the surface of the cylinder. So therefore lift is equal to lift force L or lift force F is equal to whatever it denote normally, lift force is equal to minus integral is equal to minus integral. What is PS? This complete expression, P infinity plus half rho U infinity square times of half rho U infinity square times of 1 minus circulation by 2 pi UA minus 2 sine theta whole square, 2 sine theta whole square. Okay, so this is 2 sine theta whole square into dA. So what is this area? R d theta into L. So if you take this d theta is very small, this can be approximated as a straight line. So R d theta into L is the basically this is A, R is equal to A at this point. So you can write A d theta into L times sine theta. Correct? So this is what you have here. Okay, so this is dl into sine theta. Now from this expression you have to calculate this integration little carefully by taking some important terms. Okay, so when you calculate this integration carefully, you will get the result. Let us check what is the result that you will get. Lift is equal to now A is constant, L is constant, so you can take that out. Okay, so A is constant, L is constant, so AL minus AL, of course minus A into L into integral P infinity into this sine theta d theta. Okay, and total integration is from theta equal to 0 to theta equal to 2 pi. Okay, 0 to 360 degrees total. For example, if you want to cover the total surface of the cylinder, 0 to 2 pi. So P infinity into sine theta d theta plus this half rho square into this quantity. Okay, so let us see that, half rho U infinity square into 1 into sine theta. So this is sine theta d theta minus half rho U infinity square times of 1 minus this circulation square. So circulation by 2 pi UA minus 2 sine theta whole square into this one more sine theta is again there here. So sine theta d theta. Correct? So this is what you have. So this is the total integration. Now try to understand one thing. If this P infinity is constant and this half OU square is also constant, so in this, if you split this into 3 integrals, first integral, second integral and the third integral, what is the value of this first 2 integrals? Integral 0 to 2 pi sine theta is there here in both these options. Correct? So whenever this P infinity plus half OU square is actually some constant, then please tell me what could be the total value of these two integrations. P infinity is constant and half OU square is also constant. Correct? Look, I will write one more step so that you can understand it better. Lift is equal to minus AL into this first term will actually give you. Now therefore lift is equal to minus AL integral minus AL times of theta is equal to 0 to theta equal to 2 pi P infinity times sine theta d theta plus Again, if you write this integration here, integral theta equal to 0 to theta equal to 2 pi half rho u infinity square times sin theta d theta plus, again at this point minus. Okay, so minus half integral 0 to 2 pi theta is equal to 2 pi minus half rho u square. Okay, minus you have already taken, so half rho u infinity square times of 1 minus this term, circulation by 2 pi a 2 pi ua minus 2 sin theta whole square. Okay, so this whole square times sin theta d theta. So this is the total integration value. So please tell me, whenever this p infinity is constant, if you take p infinity out, integral 0 to 2 pi sin theta d theta is equal to 0, and integral 0 to 2 pi sin cube theta, this will also be 0 actually, correct? I have given you these two expressions. So therefore, if you take p infinity out common, then this integral 0 to 2 pi p sin theta d theta is 0. So therefore, this term can be written 0. So this term is actually 0, and this term, second term, is also 0 in this integration. 0. So therefore, lift is equal to minus al into minus. So this minus multiplied with this minus, so the minus gets eliminated, a into l into. Now in this integration, this half rho u infinity square is constant. So if you take that out, half rho u infinity square. Okay, so if you take this out, half rho u infinity square, if you take out, then this capital U is also u infinity. So let us do one thing. Let us write this u infinity as u square, because free stream velocity is nothing but the u square here. Okay, so this minus and this minus got cancelled. Half rho infinity square you have written out. So we have the expression theta is equal to 0 to 2 pi 1 minus. Now circulation, this square, if you expand this square, let us see what happens. Circulation square by 4 pi square u square a square plus 4 sin square theta minus 2ab. So 4 times of sin theta into circulation by 2 pi ua into. So this is the expression for this. So this total value multiplied with sin theta d theta is what you have here. Okay, now if you see something, this is some constant term, this 4 sin square theta into sin theta. So first of all, if you see this, lift is equal to al into half rho u square into, if you split this into 3 integrals, integral theta is equal to 0 to theta equal to 2 pi, this circulation square by 4 pi square u square a square into sin theta d theta plus integral theta is equal to 0 to 2 pi 4 sin square theta into one more sin theta. So sin cube theta d theta minus, okay, there is one more minus sign. So minus integral 0 to 2 pi 4 circulation by 2 pi ua 4 circulation by 2 pi ua actually here. So this is 4 circulation by 2 pi ua into this sin theta into sin theta, which is sin square theta d theta. Okay, so you have this. Look, I think one minus sign is also missing here, right? Because when you multiply this here, half rho square into 1 minus this quantity, correct? So half rho into square into 1 minus this expression whole square, a into l you have taken out. So half rho square into this thing minus half rho u infinity square into this complete expression. So minus this minus is here. So minus half rho u infinity square into circulation term sin theta d theta. So a square plus this b square minus this value. Okay, so we have this minus into minus, we have written plus here. So plus half rho u square into integral theta equal to 2 pi this expression, correct? I think this is the correct value. Okay, Yes. Now, so this integration is 0 and this integration is also 0. So we have lift is equal to, you have to do little carefully, okay, calculations. Now AL into half rho u square into, now integration of this minus, first of all you have minus for this term which is here is actually some constant, correct? So if you simplify, for example, this is 2 circulation by pi ua is constant, 2 circulation by pi ua is constant, then integral 0 to 2 pi sine square theta d theta. Okay, so this is what you have here. Okay, so sine square theta d theta. So if you simplify some terms, then u, this square can be cancelled. Okay, then in that case what we can have, 2 and 2 can get cancelled, then a and a, radius of the cylinder, can get cancelled, then what you have, L rho u minus circulation, correct? So therefore lift is equal, I think questions came, just a minute. Okay, so fine, this is the case. So lift is equal to, therefore lift is equal to minus L rho u circulation by pi minus L u rho circulation by pi actually. Okay, so by pi actually into this integration, integral 0 to 2 pi sine square theta d theta. Okay, so this is what you have. So this is sine square theta d theta. Now if you see this case, sine square theta d theta, then what is the integration of this expression? So let us calculate that. Integral 0 to 2 pi sine square theta d theta. So this can be written as integral 0 to 2 pi 1 minus cos 2 theta by 2 d theta, correct? So sine square theta can be written as 1 minus cos 2 theta by 2. So this is equal to half times of integral 1 theta minus integration of cos 2 theta is actually sine 2 theta by 2 within the limits 0 to 2 pi, correct? So this is what you have. Now if you simplify this integration, half times of 2 pi minus 0, which is 2 pi, minus half times of sine 2 theta, so sine 4 pi minus sine 0, which is 0 actually. Okay, so this expression is 0 and this gives you actually, so this expression is actually pi. Okay, so that's how we get a expression pi here. So this integration value is actually pi. Okay, so if you write, this implies lift is equal to rho u circulation times L by pi into pi. So pi gets cancelled actually. So therefore lift force acting with a minus sign, of course. So lift force acting on the cylinder is equal to minus rho u circulation times L is what you have here. Okay, so this minus sign tells you, means basically we are calculating the vertical force. Okay, so the vertical force acting, if you change, for example, the vertical force acting in this case is minus rho u psi L. So instead of writing lift, because we got a negative value, actually we'll do one thing. Instead of writing lift, let us write FV, vertical force. Okay, you can keep vertical force acting on the cylinder. Okay, so vertical force acting on the cylinder. Vertical force acting on the cylinder. Vertical force is equal to FV is equal to, then FV is equal to FV. Okay, and this is FV basically here. Similarly here FV. So vertical force acting on the cylinder. Now this, if you see, this is minus rho u circulation times of length actually. Okay, now let us suppose this is the case when the cylinder is actually evolving in the anti-clockwise direction. Now let us suppose if the cylinder is rotating in the clockwise direction, for example, then this circulation will give a minus sign. Then in such case the force acting on the cylinder will be on the positive direction. Okay, so whenever the cylinder rotates in the right side direction, means basically in the clockwise direction, then this circulation will be taken negative. So negative of negative will give you a positive value. Okay, so therefore normally in cases we write the lift generated in case of rotating cylinder, in case of rotating cylinder. Here we got a minus sign, but we will neglect this minus sign. Why? I will tell you. So see here, this rotating cylinder is equal to rho density times u into circulation times length of the cylinder actually. Okay, so it doesn't depend upon the, okay, so this is basically rho u sigma into L, and this relation is one very important relation for calculating lift actually. Okay, look, in concept of drag force and all, I told you one thing. This is a very big derivation, so I'm just giving you the expression half CL rho AU square. Look, there when we are doing the analysis of drag force and lift force, we have two forces, pressure force and also viscous force. Okay, look, even only when the pressure force is the only thing, this is the size of the derivation. Okay, now imagine if you have also the viscous force in it, then it will be very large derivation and it involves lot of mathematical simplification. So that's why we didn't do that at our level. Okay, so anyhow, here why we have dropped this minus sign, that's the question. So here if you see this direction of flow, look, for this combination the net effect of vertical force on the cylinder is in the downward direction. Now let us suppose for the same anti-clockwise direction, if the flow is in the reverse direction. Okay, so for the same anti-clockwise direction, if the flow is in the reverse direction, then the lift will be actually positive in that case. Okay, similarly, if for the same condition, if the rotation of the cylinder is in the clockwise, then also the condition is actually in the upward direction. Okay, so therefore since the direction depends upon the value being positive or negative depends upon the sense of rotation and also the direction of this flow. So that's why we generally talk about the magnitudes, that lift generated by, in case of a rotating cylinder, is actually equal to rho u circulation times L. This is the correct expression actually. Clear? Now this effect is actually called, means the generation of lift on rotating cylinders or rotating bodies in general is called Magnus effect, because he is a German physicist actually, Magnus. So he has first studied this concept of lift generation on bodies. So this effect, generation of lift, is actually the Magnus effect. Okay, so if you share a word here, maybe one more slide I will take. Magnus effect. Magnus effect. Okay, so Magnus effect is basically generation of lift in generation of lift on rotating bodies in a fluid medium. In a fluid medium is basically the lift case. Okay, so generation of lift on rotating bodies in a fluid medium is the observation by this Magnus effect. Okay, so this is observed by Magnus. First of all, Magnus, this person is basically a German physicist and he observed this concept. First of all, German physicist. Okay, the most important thing is, many times, normally when you play cricket, this is one very important phenomena. Okay, many times if people play cricket, they might know. Let us suppose many times when people try to hit the ball, what happens is they get the thick edge and catch goes to the keeper or the slip. The reason is this Magnus effect. Okay, and basically this reverse swing is actually very dangerous and it can highly produce this Magnus effect. So that what happens is, whenever there is some lift force on the ball actually has some small mass. So whenever there is some lift force on the ball actually goes to higher height. Means let us suppose if you are expecting the ball to come to abdomen level, and if you are playing the shot, the ball comes slightly higher than the abdomen level and it hits the thick edge and goes to the catch. Okay, so normally in reverse swing, basically what happens in reverse swing, along with the swing you apply a reverse swing, so the ball actually the ball actually revolves. Okay, so whenever the ball actually rotates in the fluid medium, in air, then there is some generation of lift on the ball actually. Okay, so when you're expecting the ball to raise to the abdomen height, and if you are trying to hit a shot, then rather than abdomen height, the ball actually raises to a greater height, and actually that will, you know, hit some part of the bat which you are not supposed to hit, then that will hit and it goes for a catch. Okay, so that's why this Magnus effect, normally if you see reverse swing of a cricket ball, reverse swing of a cricket ball generates lift, okay, so all these are very dangerous applications. Okay, similarly many times you might have seen whenever people are playing golf, actually this golf ball actually in a video, in normally if you observe carefully, you might see the ball goes pitches some height actually in between. Okay, so the ball actually gains some height. Okay, you might have seen this, the ball which is actually traveling will gain some height, again try to travel. Okay, this rising of the ball is again due to this lift force, because what happens when the golf ball rotates, then in such case this actually takes place. Okay, fine. Because in reverse swing what happens, many of the times you might have seen the bowler actually holds the ball and he throws it like this. Okay, so whenever he actually takes the ball actually rotates in the vertical plane. Okay, so whenever the ball actually rotates, frankly speaking, when you are playing in this direction, wind, the crosswinds of course. Okay, so whenever crosswind is flowing, the ball is rotating, so that's why that's capable of generating the lift. Okay, that's the reason. So this generation of lift is one very important concept in sports especially. Okay, fine. So with this we close this potential flow chapter. Clear? Now tell me one thing, UI, I think you have covered fluid mechanics. Did you feel comfortable now in potential flows? No very big derivation. I mean, of course, in the last case we have some slightly lengthy derivations, but for simple cases like source, sink, vertex flows, these things we have dealt very easily, correct? Okay, so this potential flow notes will definitely help you, because even in NPTEL, if you see, you watch NPTEL, there are only 2 people in India. I mean, openly telling you, there are only 2 people in India who are teaching potential flow in complex numbers. One is Suman Chakraborty sir from IIT Kanpur, and second is me. Definitely, I can tell you this honestly, because you see many other books, even if you find textbooks and all, not even in foreign other textbooks you will see in complex numbers. Many times you see only in Cartesian coordinates with some lengthy expressions, the tan inverse of y by x plus a whole square plus b square, all these lengthy expressions, but you know, that's we are not doing here. Okay, so this is slightly a new thing that normally I don't teach of, you know, whenever I'm teaching to mechanical I didn't teach potential flows previously, but means not before joining here, but you know, if people are writing XE engineering sciences paper, then it would be definitely you know, it's a big thing that if you can solve some 2-3 questions on potential flow what comes in the exam, that will definitely help you in scoring good marks. Okay, now it's very comfortable, right? Just a bit of +1 class 11 complex numbers and slightly some trigonometry here and there, that's it. Okay, so you can easily get the things based on this. Okay, now let us, so with this we close the chapter potential flows. It took almost 5 lectures for us to talk about this, so we will discuss some problems. Okay, so 6-7 problems, I think some, I don't know, 6-7 problems I think I've kept, so let us start discussing that. Okay, so the first question, so see here, a 2-dimensional flow field is represented by phi is equal to 2xy minus x. At the point 2, 1, the value of velocity v is dash units. So let us see. Phi is equal to 2xy minus x. Now you know u is equal to dou phi by dou x. So this gives you 2y minus 1, and v is equal to dou phi by dou y, which is 2x. Correct? Just 1-2 questions are some basic questions. I just want you to play with what are the terms that are involved. That's it. Okay. So v is equal to dou phi by dou y, which is 2x actually. Okay. Now therefore, what is the point at 2, 1? U is equal to 2 times of 1 minus 1, which is 1 meters per second. And what about v? V is equal to 2 times of 2, which is 4 meters per second. So this is x component of velocity and this is y component of velocity. So if you calculate the magnitude here, therefore magnitude of velocity vector is equal to, what is the magnitude of velocity vector now? Square root of u square plus v square. Okay, so square root of 1 square plus 4 square. Okay, so this is square root of 17 actually. So if you want square root of 17, very close to 4. So meters per second, and they are also asking the answer in units. Okay, they have given some units. Fine. So square root of 17. So let us punch some keys in the calculator and tell the value. So 17 square root 4.123. 4.123 is the answer. Okay, so 4.05 to 4.2. So 4.12 is somewhere in between. So that's the correct answer. Okay, so 4.12 units is the correct answer in this case. 123. So 4.12 units is the correct answer in this case actually here. Okay, next let us go for the next case, next question. So let us see. The potential function phi flow is phi is equal to 6 times of x square minus y square, where x and y are in meters. A streamline passes through a point 2 comma 3. The correct statements are: this is point A. The magnitude of velocity at point A is 41.5 meters per second to 44.5. The magnitude of velocity at point A is 35.4 meters per second to 37.4 meters per second. Okay. Streamline passes through A is xy is equal to 6. Streamline passes through A is xy square equal to 8. So they are asking about the streamline equation and also the velocity value basically. Okay. So let us see. The potential function phi flow is phi is equal to 6 times of x square minus y square. Okay. So phi is equal to 6 times of x square minus y square. Okay, now you want the stream function actually. Okay, so let us calculate the stream function, because you know they are asking you streamline equation. Okay, so if you want streamline equation, definitely you have to calculate what is the stream function, correct? So let us calculate stream function. So how do you calculate? So the f of z is equal to u plus iv. So what is u actually? Dou phi by dou x. Okay, u plus iv is dou phi by dou x actually here. So dou phi by dou x is 12x plus I into, sorry, u, yes, f of z is u plus iv. No, this is phi plus I psi, right? This is phi plus I times of psi. So this implies f dash of z is equal to u minus iv. So if you differentiate partially with respect to x, dou phi by dou x is 12x plus I into dou psi by dou x is minus dou phi by dou y, correct? So minus dou phi by dou y is 12y. Minus dou phi by dou y is actually 12y. Okay, now if you replace this Miller-Thomson method, f dash of z is equal to 12z plus I into y plus if you have 0. So this implies f of z is equal to 6 times of z square plus constant, correct? So we have 6 times of z square plus constant actually here. So therefore if you write f of z is equal to 6 times of x plus iy whole square plus constant. Okay, so this is a complex constant, so c1 plus I times of c2 is what you can write. So 6 times of, when you expand this, x square minus y square plus I times of 2xy, that is 12 I times of 12xy plus c2. Okay, so this is what we have, and this c1 is 0 because in the velocity potential function there is no constant. So this is 0. 6 times of x square minus y square plus I times of 12xy plus c2 is there. Okay, so this is phi plus this is psi. So phi is 6x square minus y square, which is present here. So therefore psi stream function is equal to psi of x comma y is equal to 12xy plus c2. Okay, now given, so 12xy plus c2 is the stream function, so this is equal to some constant. Okay, now this is given. A streamline passes through the point 2 comma 3. Okay, so if you put 2 comma 3 here in this case, what is c2? Or generally along a streamline this 12xy plus c2 is equal to some constant, arbitrary constant. So this can say you that xy is equal to some arbitrary constant. Okay, so this is the equation of a streamline basically. Xy is equal to c dash, because this is the stream function, but along the streamline stream functions are constants. Okay, so when you take this as some arbitrary constant, xy equal to c dash is the correct streamline equation. Okay, so this is equations of streamline in this case. Equation of streamline actually. Okay, so this is equation of streamline. Now let us see, if you want, first of all, the magnitude of velocity at the point 2 comma 3. Okay, fine. So first of all you need magnitude of f of z. Yes or no? Magnitude of f of z is nothing but velocity. So what is the point at which you need? 2 comma 3. So what is 2 comma 3? This at A is nothing but f dash of z at z is equal to 2 comma 3. The point 2 comma 3 in complex plane is 2 plus 3i. Okay, so this is 2 plus 3i. So this is equal to, what is magnitude of mod f of z? 12z. So 12 times mod 2 plus 3i is what the correct answer. So 12 into, because 12 is a constant, so magnitude of 12z is nothing but 12 into modulus of this complex number 2 plus 3i. So magnitude of this is square root of 9 plus 4, 13, root 13 is what you have. Okay, so if you simplify this, your answer is in meters per second. Okay, so if you simplify this, 12 into square root of 13, square root of 13 into 12, so 43.26, 43.26 is what you have, 43.26 meters per second. So if you see, 43.26 is within this range, but this is not within this range, so that's why A is correct and B is actually wrong answer. Okay, so we have seen, just if you want magnitude of velocity at A, that's nothing but magnitude of this f dash of z complex number at this location 2 plus 3i. So we have substituted magnitude of this complex number is square root of 13, so 43.26 meters per second. Okay, now what is the streamline equation? If you put x equal to 3 and y x equal to 2 and y equal to 3, this c dash is equal to 6 at 2 comma 3, c dash is equal to 6. This implies the streamline equation is xy is equal to 6. Okay, so we have the streamline equation, xy is equal to 6. That's it. Okay, so this is wrong, xy equal to 6 is correct. Okay, so A comma D are the correct answers in this case. Clear? Simple question. You can easily calculate stream function, all these things. Once you apply this simple analysis, then everything is simple here. Okay, nothing big to worry. Okay, next, third question. The potential lines in case of a doublet. So if you see the doublet, we have seen that doublet is something like this. Doublet, f of z is c by z. Okay, and the potential and streamlines we have done. So here if you see, we have seen clearly these are streamlines. Okay, so these are the streamlines. So these are streamlines actually, correct? We have seen them. So all these things, they are streamlines. Now we have seen the equipotential lines also, correct? So equipotential lines are something like this. They are tangents to so we have the equipotential lines something like this, correct? We have done this graph already. See, definitely previously when you are trying to see this kind of diagrams, you might have got panicked, but now they are very easy and you are playing, correct? Fine. So these are equipotential lines in this case. Okay, so here if you see, these are the equipotential lines. They are the equipotential lines. Okay, so equipotential lines are basically tangents to y axis. This is x and this is y, minus x and minus y. Okay, so these are the tangents to y axis. Okay, so these circles are basically equipotential lines are tangents to y axis, correct? So we have seen this. Equipotential lines are circles tangent to x axis. No, these are streamlines. Circles tangent to y axis with center on x axis. Yes, this is correct. Concentric circles. No, first of all, they are not concentric circles in both the cases. Okay, so B is the correct answer. Okay, so B is the correct answer in this case. So let's go for the next question. A two-dimensional source of strength 1.8 meters square per second has been placed at the horizon in the stream of inviscid and incompressible fluid moving with a uniform velocity of 0.6 meters per second. The resultant velocity of the fluid in mm per second at r equal to 0.75 meters and theta equal to 120 degrees. Okay, so you will get some point when r is equal to 0.75 meters and theta equal to 120 degrees. You will get some point. So at that particular point, what is this velocity, resultant velocity? Okay, so let us take that. So first of all, let us write, this is a superposition, correct? So what is f of z? There is a source of strength 1.8 meter square per second. So m by 2 pi times this is placed at origin, correct? When it is placed at origin, directly log z to the base e, log z to the base e, plus there is also some uniform flow. What is that uniform flow? In the stream of inviscid fluid moving at a uniform velocity of 0.6 meters per second. So this is 0.6 times z. This is uniform flow, correct? Now the resultant velocity of the fluid at r equal to 0.75 meters, at r is equal to 0.75 meters, 0.75 meters and theta is equal to 120 degrees. So please tell me this potential function. It is very easy to write this, yes or no? Now if you want velocity, what you will do? F dash of z is equal to, if you differentiate this, 1.8 by 2 pi times integration of ln z is 1 by z plus differentiation of log z is 1 by z plus 0.6. Okay, so this is the value. Now you want the resultant magnitude, means you want the magnitude of this complex number. Okay, and first of all, if this is the function, they are asking you in polar coordinates, correct? So we'll do one thing. First of all, let us write this z value as r into e power minus I theta on the top. Okay, so this is equal to magnitude of 1.8 by 2 pi r into e power minus I theta plus 0.6 magnitude, correct? So this is what you have here. Okay, so we have 1.8 by 2 pi r into e power minus I theta plus 0.6. When you want magnitude of this f dash of z, actually this z value is given by this particular complex number, r equal to something and theta equal to something. Okay, so from this two you can frame the value of z, actually r into e power I theta 2 pi by 3. Okay, so this is the value anyhow. So if you replace it here, then we get 1.8 by 2 pi this z directly. If you write, then we have this expressions. So what we'll do is we will split this actually. Okay, so if you split this, magnitude of 1.8 by 2 pi r into cos theta minus I times of sin theta, so minus I times of 1.8 by 2 pi r sin theta plus 0.6. This is the complex number, correct? So if you see 1.8 plus 0.6 is the real part, so this is equal to magnitude of 1.8 by 2 pi r cos theta. Okay, so 2 pi r cos theta plus 0.6 minus I times of 1.8 by 2 pi r sin theta. So we have this value. So this is the complex number for which you have to calculate the magnitude. Okay, so replace r is equal to 0.75 and theta equal to 120 degrees. Okay, so if you replace this 1.8 by 2 into 0.75, 1.5 times pi cos theta. So what about cos theta? Cos 120 is minus 1 by 2 plus 0.6 minus I times of 1.8 by 1.5 pi into sin 120 is root 3 by 2. So this is what you have here. Okay, so now we can do the calculation. So this 2 can cancel out this 0.9 times and 0.3 table can cancel this 3 by 5 times. Okay, so 3 by 5 is again 0.6. So 0.6 by pi, and there is a minus sign here. So 0.6 minus 0.6 by pi is the real part. 0.6 minus 0.6 by pi is the real part of the complex number plus I times of, or minus I times of this value is again 0.9 and 3 table 3 0.3 table 3 and 5 times. So 3 by 5 pi. This is the complex numbers magnitude. Okay, so you can just calculate this value. So if you calculate this value, you can get the answer easily. Okay, so let us calculate 0.6 minus 0.6 by pi whole square, 0.6 minus 0.6 by pi. So this value, so this is the real part. So square of this plus plus 3 root 3 by 5 pi whole square. So 3 into square root of 3 by 5 pi. So plus 3 into square root of 3 by 5 pi. Okay. So by 5 pi. So if you close this, then square of this. So take a square root 0.526, correct? So 0.526 meters per second. Okay, so 0.526. The magnitude of this complex number is 0.526 meters per second almost. Okay, so we got 0.5260. Okay, so in mm, if you see this is in meters per second, so if you shift this, this is 0.526 mm per second. That's it. Okay, the only thing is you have to calculate the magnitude of the complex number, but since this is not in direct form a plus ib form, you have converted that to a plus ib form in some 4 steps, 1 2 3 4. Some simplification is done in between. So 0.526 meters per second is the correct answer, which is 526 mm per second. Okay, clear? Then let's see this question. Something is given. The stream function psi for uniform flow past a circular cylinder radius in polar coordinates is given by psi is equal to 8 times of 1 minus a square by r square into r sin theta. Okay, the resultant velocity on the cylinder at theta equal to 90 degrees is dash units. So they have given you the stream function. Okay, so stream function is given to you and they are asking you the resultant velocity. Okay, so this is r sin theta, but I think here psi is equal to 8 times of 1 minus a square by r square into r sin theta. Is this r there in our questions? I think this r is not there, no? Or it's there. Stream function, right? So r minus a square by r. Okay, fine, it is there. And let us keep that. Okay, so stream function is given to you for flow past a cylinder. Given psi of r comma theta. Psi of r comma theta is equal to 8 times of 1 minus a square by small r square into r sin theta. So this you can write as 8 times of r minus a square by r times of sin theta. Okay, you multiply this. Now this is stream function. So here if you see, we want the resultant velocity. How do you calculate the resultant velocity here? You need to calculate resultant velocity at theta equal to 90 and on the surface of the cylinder. Okay, so r is equal to a, at r is equal to a and theta equal to 90 degrees. This is what they are asking you. Okay, so at r is equal to a on, because they told the resultant velocity on the cylinder at theta equal to 90. Okay, so what is the resultant velocity? This is what they want. So what is the expression for u theta? U theta. How do you calculate this u theta from the stream function? Okay, so we know on top of cylinder at r is equal to a and theta equal to 90, magnitude of v is nothing but magnitude of u theta. Okay, so how do you calculate this u theta expression? So let us see here. So that's why u r is equal to 0. So we have to calculate expression for u theta. I told you many times that this f of z, if you take this, look, even in exam, if you forget, I am telling you how you will write that. 5 plus I times of psi, correct? When you differentiate with respect to r, f dash of z into e power I theta will be equal to dou phi by dou r plus I times of dou psi by dou r, correct? So we are writing this as u r minus I times of u theta. Then definitely you can easily understand from this relations that u r is dou phi by dou r, u theta is minus dou psi by dou r. That's it. Okay, so that's how you will actually do this. Clear? This minus dou psi by dou r. In exams and all, if you forget this Cauchy-Riemann equations and all, you can use this simple understanding to get what is radial velocity dou phi by dou r and what is this u theta, which is minus dou psi by dou r. Clear? Okay, just I want to check whether you are raising the notes or not. Fine. So that's how you will actually check in exams if you don't get this. So fine. Anyhow, u theta is equal to, therefore u theta is equal to minus dou psi by dou r. So this is equal to, look, minus, see, you see the things here. Actually they have given this function r separately. Look, let us suppose now if you try to differentiate this partially, you have to do uv rule. You have to, because this is product of two functions. But if you multiply this r inside, it is a simple thing. Okay, so minus 8 sin theta are constants, 8 into sin theta into differentiation of r minus 1 minus a square by differentiation of 1 by r is minus 1 by r square, so that makes you plus. Now since they are asking you on the top of the cylinder, this radius value is equal to a because on the cylinder, so this is equal to minus 8 times of sin theta into 2, which is minus 16 times sin theta. Okay, 16 times sin theta. So therefore at theta equal to pi by 2, at theta equal to pi by 2, magnitude of u theta is 16. That's it. Okay, so 16 is what you have. So this answer is 16 because 16 into sin 90, sin 90 is 1, so minus 16 is what you have. So taking magnitude of that value gives you 16 as the correct answer. Okay, so 16 is what you have as the correct answer. So 15.5 to 16.5, 16 units is the correct answer. That's it. Okay, normally in exams and all, if you forget this, you can use simply just to know the relations. What is UR, what is U theta, all these things. Okay, fine. Okay, I hope it's clear. Let's go for the next question. A source at the origin, and a uniform flow at 5 meters per second are superimposed. So obviously this gives a Rankine half body. The half body which is formed has a maximum width of 2 meters. The width of the body at the origin. Tell me what is the answer? I close this. Yeah, it is directly given. So tell me what is the answer. They are given maximum width is 2. Then at origin what is the width? They are asking you. In yesterday's class we have seen. If you remember, look. For example, if you superimpose source plus uniform flow, this gives to the case of a Rankine half body. So this gives to the case of a Rankine half body. Correct? Yes, half of maximum, which is half of 2 is 1. Okay. So now if you see, we have plotted the streamline actually. The Rankine half body we have seen. So if this is x-axis, for example, and if this is y-axis, then we have seen this half body will take this particular shape, and similarly this like. Okay, now the maximum width at this section, this is the maximum width of the Rankine body. So the maximum width at this section is m by u actually here. Okay, and we have seen at this section at the origin, this height is half of this value. Correct? We have seen this. We have discussed about this a lot of times in yesterday's class. So this is m by 2u. Okay, so that's it. This width at this location is half of the total width. Okay, so this is given 2, this is 1. That's it. Simple. Correct? So this value is m by 2 pi u is what we have seen. M by 2 pi u is what we have seen. Okay, so these are the dimensions that we have seen basically. So therefore at origin, width at origin is equal to half times of maximum width. Okay, so this is half of maximum width. So what is the maximum width actually? 2 meters, right? They have given maximum width of 2 meters. So the correct answer is 1 meter. That's it. Okay, so this is 1 in meters. So 1 to 1 is the answer. Simple. Okay, imagine doing this question without knowing complex numbers and without knowing this concept of Rankine half body. How much time it will take in exam? Almost some 30 minutes. Yes or no? Correct? You have to write the tan inverse of that expression. Okay, because source is there, so you write the stream function plus I times of tan inverse, all these things. Then by the time you write all these things, get exam gets finished. Okay, so that should not happen. Okay, so this is the case, half times of maximum width, which is 1 meter. Okay, that's the correct answer and simple answer for this question. So let us see. The velocity field for a free vertex in the r theta plane is given by v bar is equal to c by r times of e theta, of course, along a line of constant theta. Of course, if c is equal to 0.3 meter square per second, then the volume flow rate or unit depth between r1 is equal to pi unit depth at r1 equal to 0.2 meters and r2 is equal to 0.224 meters is dash meter cube per second per unit depth actually. Okay, so let us see, there is some vertex. First of all, there is some vertex. Now whenever there is some vertex, R is equal to R1, and let us say this is R is equal to R2. Depth into the cylinder is depth into the plane of the board is 1 meter. Okay, so depth is equal to 1 meter. Now what you need actually, if you see this flow is coming in this direction, so V theta is equal to C by R is what you have here. Okay, so V theta is C by R. So whenever V theta is C by R, look, we have to calculate the flow rate. Okay, so flow rate is equal to flow area multiplied with flow rate is equal to flow area multiplied with the velocity. Okay, so what we'll do is, since this velocity means if you take velocity at these two sections, it is not same. At these three sections the velocity is not same, so therefore you take some small element, some small elemental strip you take. So small elemental strip you take here, for example. Okay, so you take the small elemental strip because velocity can remain constant only within this small strip that you take. Okay, now this area is equal to, if this is at a radius of smaller, then this dA is 2 pi r into 1. Okay, so this is because 1 unit depth, so 2 pi r into 1. So through this the flow is actually at V theta is equal to C by R. Okay, so what is the discharge? Q is equal to V theta into this is 2 pi r into dr, correct? So this is 2 pi r, dr is the area that's available. So 2 pi r dr is what you have. So 2 pi r dr is the area in this case. So therefore V theta into dA integration over the complete area. So Q is equal to integral V theta is C by R into dA is 2 pi smaller dr. Okay, this within the limits R1 to R2 actually. Okay, so if you do, then what happens, this R and R gets cancelled. So 2 pi times constant into R2 minus R1. 2 pi times this constant times R2 minus R1. So this is meter cube per second per unit meter. Okay, because you see this area is 2 pi r dr and we have this unit width. So Q is equal to 2 pi into what is the value of C? 0.3. So 0.3 times R2 minus R1. So the difference between these two is 0.04. 0.04 actually. Okay, so this is going to be your Q in meter cube per second per meter. Okay, so this is what you have. So if you simplify, 0.6 into 0.04 into pi, 0.6 into 0.04 into pi. Okay, so if you simplify this, 0.0754, 0.0754. Okay, so 576 came here, 0.0754. Did we make some mistake here? So what about the flow area? Actually this is a vertex, correct? So particles are actually evolving. Okay, just a minute here. Flow doesn't travel in this direction, na? Flow actually rotates, correct? Yes or no? Flow actually, what happens? Flow actually will rotate like this, correct? So whenever flow is rotating, then definitely this is only dr. This is not 2 pi r dr. Sorry, this expression goes wrong. Then I was thinking of the pipeline actually. Okay, sorry. So see here, what we are trying to take is, look, they are asking the flow rate in the vertex, correct? So when they are asking the flow rate in the vertex, see, flow happens in this direction. Okay, so whenever flow happens in this direction, what we'll do, we will take some small elemental strip and we will try to calculate the flow that's happening through this region. Okay, so there is some flow which actually comes out. Okay, so there is some flow which actually comes like this. So what is this thickness? dr into length. The perpendicular length of the for the flow area is 1 unit. Okay, so dA is equal to this dr into 1. This is what we have, dr into 1. Okay, because you see, whenever the flow is traveling in this particular direction, then the flow area available is this difference in dr into multiplied with this length of the plate, length of this particular thing, okay, which is 1 unit in this case. Okay, so this is dr is what given here. So dA is equal to dr times 1, and here again you have this is r1 and this is r2. So in that case we can write integral v theta is c by r into dA is dr times 1. Okay, so this is what you have, r1 to r2. This is the correct expression, because in a case of a vortex, flow actually rotates. Okay, flow doesn't travel in the direction, so flow actually rotates. So the area which is normal to the flow is going to be this area, which is the plane wall kind of thing here. So that dr multiplied with the thickness of that gives you the area. So if you integrate this, c times ln r2 by r1, of course. Okay, so because you see integration of 1 by r dr is ln r, so r1 to r2, c times of ln r2 by r1. Okay, so this implies your discharge q is equal to c, which is 0.3 times of ln r2 by r1. So 0.24 by 0.2, 0.24 by 0.2. This could be the correct answer in this case. Okay, so if you simplify this, q is equal to, this is in meter cube per second, but of course per unit meter depth of that particular vertex. Okay, so if you simplify this value, 0.24 by 0.2, 0.24 by 0.2, 0.12 of course, so 1.2, 0.24 by 0.2, so 1.2 logarithm of this ln into 0.3, so total 0.0547. okay, 69 if you round off, 547, 0.0547, 0.0547 meter cube per second per meter. Okay, so this is what you have here. Okay, so 0.0547 meter cube per second. Clear? So 0.054 is in between this. Okay, so this is the correct answer. Obviously, because if you see, in case of vertex, flow doesn't travel along the pipe direction, no? It actually rotates. So whenever this is rotating, the perpendicular area to the flow will be this small section. So dr multiplied with width of the vertex actually. Okay, so that's 1 unit. So 0.0547 meter cube per second per meter is the correct answer. Yes, fine. So did you all understand this potential flows clearly? Okay, I think this is the last slide maybe. Yeah, I think that's the case. Okay, so if you try to write the summary of these things, superpositions. So we have seen uniform flow, summary of superpositions, so in this summary of superpositions, first thing we have done is uniform flow plus source. We got the case of flow past a half body, which is called Rankine half body. This is Rankine half body. Then in the second case, we have seen this source plus sink combination, which is doublet, of course. Okay, so uniform flow plus doublet. So this gave us flow past a stationary cylinder. So this gives us flow past a stationary cylinder. Flow past a stationary cylinder. So this we have seen actually, and normally this is flow past a stationary cylinder. Okay, instead of doublet, if you have uniform flow plus source plus sink, source can be at any strength, sink can be at another strength, and they need not be very close also. Okay, so in such case, source plus sink if you have, then they have the contribution for the Rankine oval. Like in this case we have a half body, in this case we will get a oval actually. Instead of here we got a streamline to be circle, so in such case we get oval. Okay, so this is the case of Rankine oval actually. And fourth, if you see, uniform flow plus doublet, uniform flow plus doublet plus, okay, so uniform flow plus doublet plus vertex. You have taken the vertex also. So this gave you the case of flow past a rotating cylinder. Flow past a rotating cylinder. Okay, so flow past a rotating cylinder. So these are, of course, we haven't discussed in detail about this, but normally the complex potential function is again same. Okay, how will you write uz plus m by 2 pi m1 by 2 pi log z minus z1 m2 minus m2 by 2 pi log z minus z2, some wherever they give you strengths and vertexes. Okay, but calculation of stagnation points, all these things you know now how to calculate. Okay, the complex number where that f dash of z is 0 is the location of the stagnation point. We have seen in the calculations of Rankine half body, all these things. Clear? Yes. So with this we conclude this chapter completely. Then we have one last chapter which is the, okay fine, so we have one last chapter which is the basics of compressible flow actually here. Okay, so basics of compressible flow we have taken as that's the recently introduced chapter into the syllabus 2 years back, 2021 GATE they have introduced, and it's a very small chapter actually. Okay, so almost some 2 to 3 hours of duration it takes. Okay, so almost 1-2 lectures is what it needs actually, so to talk about the GATE syllabus. But normally speaking, compressible flows is a very good subject. Okay, even in my MTech I was doing some of my courses on compressible or advanced gas dynamics courses. So if you see, that's a very elaborative course actually. Okay, normally all the rocket science, that's the basic fundamental for the rocket science. Okay, not generally any high speed vehicles, you see missiles, all these things, in all these cases that compressible flows is one very important fundamental subject that people deal with. And in that there are many other subjects also, advanced subjects, advanced gas dynamics. Okay, we have a lot of things like that. Okay, then this we will discuss maybe in the tomorrow, that extra session 4 p.m. to 7 p.m. Okay, so first what we'll do now is, this is the major portion of the syllabus that we have covered, both mechanical and also XC. Okay, so once please open the first page of your notebook. I think you might have got a fat notebook by now, so definitely open the first page of the notebook. We will quickly revise what we have learned actually. Okay, because the syllabus got completed, so we will have a quick revision of what we have learned right from the first chapter to this potential flow chapter. Okay, so in the first beginning of the class, means in the first lecture, we have defined very simple things like what is fluid, what is solid, okay, what is mechanics. We have seen the classification of mechanics and all. Okay, so in fluid, so we have started with the discussion of what is fluid, what is solid, how to differentiate between solid and fluid. These general talks were done actually. Then we came to know that fluids are the substances which actually deform continuously under action of even small shear stress. If you apply, then definitely the fluid starts deforming continuously. Okay, so people initially didn't understood what is this continuous deformation. Then I've told you again clearly. Okay, so once we talked about that, since the deformation is continuous, shear strain is directly proportional to the rate of the shear strain. This is given by Newton's law of viscosity, that shear stress acting on any layer in a fluid is proportional to the rate of rate of shear strain of the element. Okay, so this is Newton's law of viscosity. So we have seen in one special case which is called the co-ed flow, there is some linear variation of fluid velocity. Then we observed that the shear strain rate is actually equal to the velocity gradient in the y direction. Okay, so from then onwards we started observing d gamma by dt is du by dy. Okay, but actually it is d gamma by dt. Then we have seen the applications of few things, like for example we have talked about the application of Newton's law of viscosity, like pulling shafts, rotating shafts. Okay, then pulling some sleeves, all these things we have talked about. Then we talked about the concepts of compressibility and bulk modulus, which are very important properties in fact. Okay, so compressibility and bulk modulus, if you see, we have a lot of things there. Compressibility is basically the measure of compressibleness of a system. Bulk modulus is reciprocal of that. And if you want to observe whether a fluid is incompressible or not, you have to go for the bulk modulus value. Okay, but whereas if you want to observe whether a flow is incompressible or not, you need to look for this Mach number. Okay, so generally Mach less than 0.3 312 is the range, or 315 sometimes. 323.33 is also allowed sometimes. Okay, so that's the range for identifying the incompressibleness to compressibleness of a flow actually. Okay, so then we talked about the types of fluids: Newtonian fluids, non-Newtonian fluids. Okay, rheology. So we have talked about two types of fluids: fluids which deform, means whose deformation rates can affect the viscosity, and similarly with the time what viscosity happens. Okay, so we have seen plenty of examples there. I have given you some examples there. Then we started looking at this concept of surface tension and capillarity. Okay, so concept of surface tension and capillarity is, again, capillarity is one of the consequence of surface tension. So surface tension is not a single property, it's basically some binary property that depends on a lot of things, like the type of fluid, type of surrounding medium, type of the solid the fluid came in contact. Okay, there comes a lot of things actually. Okay, so we have seen the consequences of this surface tension. Like normally if you take a droplet, if rain is coming, the droplets are spherical in shape. Okay, we know all these things. Okay, washing clothes with hot water makes cleaning easy. Putting detergents will make cleaning much better. Why these things are happening, we are telling, we have talked about in terms of surface tension. Okay, then we have seen the applications of surface tension, capillarity. Then we have detected some expressions for capillary rise and capillary fall is what we have seen. So with that we finished the first chapter. So in the second chapter we have seen the Pascal's law. So Pascal's law is basically that in a static fluid at a particular point, pressure is uniform in all the directions. Okay, and then we have seen the hydrostatic law, x bar minus del p by O is equal to 0. Okay, so we have seen that equations, we derived all these equations actually. Then using this hydrostatic law, we observed the pressure variations, the variation of pressure with depth in different fluids. For example, in case of incompressible fluids, the variation is linear. In case of isothermal compressible fluids, it is exponential in relation, and in case of non-isothermal compressible fluid, it is power law kind of variation generally. Okay, then we talked about manometers, why there are different types of manometers, what is the simplest construction of manometer, like piezometer basically. So from piezometer we have started a discussion and we moved on to a great extent, like inclined tube manometers, then after evolution of this differential tube manometers, then from differential tube to inverted tube, how inverted tube manometers are better than the differential tube manometers. We have talked about all these things. Then we slowly moved on to the hydrostatic forces. Okay, so whenever you keep any surface, if we have split that chapter into two parts basically, plane surfaces and curved surfaces. Okay, so we have seen if you keep any plane surface in fluid, what is the hydrostatic force that's acting. We have calculated some formulas there, rho g h into a bar, all a into h bar, all these things. Similarly we have calculated the concept of we have defined concept of center of pressure, and then we derived certain expressions. It's not a big derivation, very simple, taking moments and all and equating will give you the depth of center of pressure, okay, acting on any surface. That again we have done some analysis on curved surfaces. We have again talked about projections of areas, okay, and how to write the hydrostatic forces in different things. We have talked about them. Then in the fourth chapter we talked about buoyancy and flotation. So normally whenever there is some hydrostatic force on the surface, then what is the hydrostatic force on the body? This is what our point of discussion at that time. So we talked about this hydrostatic forces on this bodies, actually buoyancy. Then we started looking at stable equilibriums, both in case of floating bodies and also in submerged bodies. So in case of, firstly we took about submerged bodies, things are very simple in that. So in case of completely submerged bodies, if the body has to be in stable equilibrium, then we know that center of gravity of that body should lie below the center of buoyancy. Okay, and similarly if unstable, then definitely G lies above the center of buoyancy. We talked about that. And in case of floating bodies, we have seen clearly this concept of center of buoyancy and center of gravity is not alone sufficient to talk about stable equilibrium. Then we defined one point which is called the metacenter. So metacenter is generally the point about which the body oscillates. Then we have done certain analysis on calculation of metacenter, metacentric radius, moment of inertia. Okay, we talked about submerged volumes, all these things. We have solved some good number of examples and DPPs on that as well. And then after we moved on to the concept of a ship actually. Okay, so what happens in case of a ship, basically about pitching and rolling, out of those two, which is very important in design point of view. Okay, then what is the difference between passenger ship and a cruise? Means basically if you see this carrier, or basically this goods carrying ships, cargo ships, we have seen the difference in terms of time period and stability. We came to know that time period of oscillation and stability, both are two different parameters actually. So we talked about them. Then we moved on to we calculated metacentric heights experimentally and all. Then we started analyzing the fluid systems. Okay, so to analyze fluid systems we have taken two approaches basically, Lagrangian and Eulerian approach, but since Lagrangian is mathematically very complicated, we go for the Eulerian approach, because following large number of particles individually is very, not a very easy thing. So that's why we have talked about Eulerian approach, which is position based approach. Okay, so in differential analysis, we taken, whenever there is a flow, we have taken some small part of the element and we have done certain analysis. Okay, so we have derived the expressions for acceleration. Okay, acceleration vector. Then we have seen accelerations of two types: local acceleration and convective acceleration. We discussed all these things. Okay, so once the acceleration terms are done in Cartesian coordinates, we have seen in polar coordinates also. So from there we have seen the concept of this translation, rotation and deformation of fluid bodies. Okay, they have derived the concept of angular velocity from there. Okay, linear strain rates, shear strain rates, we have made a lot of discussion on that. Okay, we have derived some formulas: linear strain rate, for example, in x direction dou u by dou x, in y direction dou u by dou y. Similarly, expressions for shear strain rates, expressions for this angular velocity, we have talked about these things. Then we see some flow visualization lines, like for example streamlines, path lines, okay, streak lines and timelines and all. We have seen how to come at the equations of these lines actually. And then from there we moved on to some concepts of continuity equation, mass conservation basically, and from mass conservation in both Cartesian and polar. So then after we moved on to conservation of momentum in Euler's equation basically. Okay, so in Euler's equation, so after Euler's equation we talked about this uniform translation of fluid bodies. Okay, like for example, if some fluid is moving as a bulk motion, then means without actual flow, if the fluid is filled in some container or something, and if the container is moving, then what to do, we have seen actually. So these things we have observed. And then after that we have seen some differential analysis on vertex flows, rotational flows, irrotational flows, because basically by using Euler's equation we have derived Bernoulli's equation. Correct? Euler's equation, if you apply along a streamline of a flow, you will get Bernoulli's equation. We have seen Bernoulli's equation, and then we moved on to the concept of this Bernoulli's equation, this vertex flows. Then we observed one very, very important result, that in case of irrotational flow you can apply Bernoulli's equation at any 2 points in the flow, but in case of rotational flow you can apply Bernoulli's only at 2 points along the same streamline. Okay, so that we have observed. And after that we have seen like what is the main difference between irrotational and rotational flows and all these things. Then we have talked a bit of projectile motion also at the end. So that concluded our differential analysis of fluid systems. Then we started looking at control volume analysis of fluid systems. So in control volume analysis we have seen basically this Reynolds transport theorem, which is one very fantastic theorem for connecting property changes of system to the property change of any quantity change of a control volume. Okay, so using that we have detected this continuity equation, means basically continuity equation, momentum equation, and also the angular momentum equation, mass conservation, momentum conservation, and angular momentum conservation equations. Then we applied them for different applications like fluid jets, okay, lawn sprinklers, many applications actually we have applied them. And from there we moved on to the case of tanks actually. Okay, so time for emptying tanks. Okay, this projectile motion, again in case of tanks we have seen if tank has some small hole, what is the range of the projectile. We have talked about all these things. Okay, and yeah, basically these are the things that we talked about there. So from there we started putting some trouble to us. We have kept viscosity into the picture. So in incompressible viscous flows, means basically internal viscous flows, we have derived the Navier-Stokes equation, some mathematical things we have done there. So we have seen normally this Navier-Stokes equation don't have any exact solution, but for 4 simple cases we have solved the Navier-Stokes equation where majority of the terms are zeros actually. Okay, so firstly we have started with co-ed flow. So in case of co-ed flow we have one plate fixed and one plate moving actually. Okay, now in co-ed flow there could be possibility that somewhere in between the top and bottom plates the fluid layer can move with a velocity higher than the free stream velocity. Sometimes they could also be lower than the free stream velocity. Okay, means the top plate velocity. Then we have seen one thing which is called the dimensionless pressure gradient, which is alpha. So alpha is equal to some, at that nomenclature, h square by 2 mu u infinity into minus dp by dx is what we have seen. And then from there we have talked about this equations like we have seen when alpha equal to minus 3 at any given section the net flow is 0. Okay, so we have seen that this point is very important actually, at alpha equal to minus 3. So from there we moved on to the case of plane Poiseuille flow, means basically flow between 2 fixed plates. We have taken some analysis and we have seen the average velocity to the maximum velocity is 2 by 3 in that plane Poiseuille case. Then we have applied the Navier-Stokes equation in polar coordinates for this Hagen-Poiseuille flow, which is flow through pipes, of course. So in case of this flow through pipes, we have seen again the average to maximum velocity is 1/2. We have deducted some velocity profile, and finally I have shown you thin film flows also. Okay, so we have a thin film flow we have talked about, and that thin film flows we have seen certain importance for XE examination also. So with that we finished this internal viscous flows. Then we came back to this pipe flow. Okay, then we derived the expressions for pressure drop in a pipe of length L. Okay, dash is friction factor, how to calculate the pressure losses, pipes in series, parallel. We have talked about a lot of things there. Darcy-Weisbach equation. Okay, then we started looking at external viscous flows. Okay, so in case of external viscous flows, so whenever the fluid is flowing over the flat plate or generally on top of any body, what are the how actually the boundary layer gets developed actually on the case, what is the favorable conditions for boundary layer to develop actually. Okay, which is nothing but normal pressure gradient, del P by del X should be negative in that case. Okay, so we have seen normally within the boundary layer the pressure is actually constant at all the points. We have seen that using the non-dimensionalization of the equations, and we have talked about initially in the external flows about the displacement thickness, momentum thickness, kinetic energy thickness, all these parameters. Then we have derived the one Kamen's momentum integral equation, which is a bit important. So tau W by rho U square is equal to dou theta by dou X. We have seen that because that is the actual equation which gives you the expression for delta boundary layer thickness in terms of known parameters like fluid viscosity, fluid density, X from the leading edge. We have seen that. Okay, so from there we started looking at this non-dimensionalization concepts. Okay, then Blasius solution, we have seen Blasius solution is 5x by iota ix. We have seen that. Okay, then non-dimensionalization, all these things, and then we moved on to this concept of drag and lift. We have seen normally in case of drag there are two types, form drag and friction drag actually. So form drag is due to the pressure and friction drag is due to the viscosity effects. Okay, so we have seen them, and we have given certain expressions for calculation of drag and lift forces. Okay, we have seen the concept of terminal velocity. Normally if you leave a sphere, how you actually calculate the kinematic viscosity of a fluid using the Stokes experiment. We have seen Stokes law we have derived. Normally for the sphere the Reynolds the coefficient of drag is 24 by Reynolds number. So if you apply that we got the answer. Then after that we moved on to turbulent flows, which is a very small chapter actually. So this turbulent flows actually, if you see in case of turbulent flows, we have seen certain things like the velocity profile, which is logarithmic, but within the sublaminar layer, which is very small, the velocity profile is linear. Then shear stress variations. Okay, we have seen certain velocity variations. Okay, and we have talked about smooth and rough pipes, how to calculate the phase time velocity, average velocities. We have talked about how to calculate the friction factors. If some empirical relation is given, how to use that. We have seen all these things in the turbulent flows, and we have seen the fluctuating component of velocity. Average of the fluctuating component is 0 in case of turbulent flows. So from there we entered dimensional analysis, which is one very important chapter and fundamental chapter actually. Okay, so principle of dimensional homogeneity has to be valid definitely between any equation. Okay, so using this principle we actually talked about two methods, like one is the Rayleigh's method and second is the Buckingham's Pythagorean method. So in case of Rayleigh's method, we have seen that we depend on the power law variation, and in case of Buckingham Pythagorean method, we depend upon the variation, we depend upon the number of pi terms. Okay, so we have seen in detail these two methods, and also in using Buckingham Pythagorean method I gave you general terms, general non-dimensional terms which are to be made equal for any hydraulic machine. Okay, so we have talked about that also, and then some important dimensionless numbers we have talked, and then we have solved some numericals. Then after that we started this potential flow chapter, which is one very important chapter again. Normally in books and all you feel this very complicated and clumsy, but I think these 5 videos whatever we have done, these will be definitely available, will be definitely helpful for you in understanding the potential flows in a much easier sense actually. Okay, so we have seen the conversion of Cartesian to polar coordinates. We have seen what is analytic function, what is complex potential function. Then for basic flows, how do you develop the complex potential functions. For superpositions, what can be done. In case of superpositions, velocities and complex potential functions, all this can be superimposed, but pressures cannot be superimposed. Okay, pressures can be solved only using Bernoulli's equation. Okay, so we have seen all these things. So these are the things that we basically talked about. Okay, and in today's class the generation of lift, Magnus effect and all, they are important. And normally in case of rotating cylinders you don't have the fixed number of stagnation points. Sometimes it can be 2, sometimes it can be 1, depending upon the type of, depending upon the rotational speed of the cylinder actually. Okay, so if the rotational speed of the cylinder is such way that the tangential velocity v theta is 2 times of the phase time velocity of the air, then in such case you have only one stagnation point. Okay, so these things has to be understood little carefully. So this is the complete fluid mechanics that I have taught you in this past 1.5 months I think. Okay, so fine then, thank you all. We'll meet again tomorrow at 4 p.m. for that small discussion on basics of compressible flow, because that actually I thought of teaching you after thermodynamics is taught to you, because we need some thermodynamics things in basics of compressible flow actually. But anyhow, we'll keep that in this fluid mechanics course itself, and we will discuss that. Okay, no issue. Thank you all.